Hi, I'm Forrest Speed from the University of Colorado, and it's actually my second talk at a conference before, and the first time I was so nervous that I couldn't open the PowerPoint. My hands were shaking, and this time it seems that we're doing a lot better, so things are going well. So I'm working on a team that's end goal is to perform voltage imaging in freely moving animals. So there's quite a bit that goes into that, and right now I'm showing the SimScope 3D, which is our current design for a miniature structured illumination microscope, and micro-LED stripe arrays that are being fabricated by our collaborators at Columbia University to put on board to essentially supply the power and structured illumination that we'll need for voltage imaging. And so the reason that we're using a wide field structured illumination technique, I might have touched on it earlier, is that in two photon you have inherent optical sectioning, while in wide field you do not. So your signal is contaminated by out of focus fluorescence, but if you use structured illumination, you're able to essentially encode in focus information and then extract it from out of focus information. So this is really based on a technique called optical sectioning structured illumination microscopy. And so in this technique, a high frequency grading pattern is projected onto this sample. And so that grading pattern is only modulates in focus information and not out of focus information. So you can demodulate it using square law detection. And you can also obtain a pseudo wide field reconstruction by taking essentially the mean of those three images. But as we are looking for the techniques for voltage imaging, we want to go as fast as possible. So the next technique that came out is called halomicroscopy. So in halomicroscopy, we're able to demodulate the in-focus and out-of-focus information from simply a structured illumination image and a uniform illumination image. And so based on analysis of a difference image, you can extract low-frequency in-focus information and combine that with a high-pass filtered version of the uniform illumination image. Unfortunately, our micro-LED arrays can't quickly switch between uniform illumination and structured illumination, so we're unable to perform this technique. So the next best thing that we tried is called structured illumination microscopy with interleaf reconstruction. So in a normal structured illumination or OSM, you essentially obtain one OSM image per every 3 images. And so what the interleaf reconstruction technique does is it fills in those extra frames. If you think about it, each image is really just phase shifted 120 degrees from each other. So essentially, you can get an OSM image for each raw frame. Of course, you have to think about this as each frame is being used 3 times, so it's very similar to a boxcar average, so it's not a completely lossless method. The next 2 techniques that I want to look at both have been used for voltage imaging. In vivo, unfortunately, they're not compatible with our micro LED stripe arrays, which is why we haven't tested them so far. So the next technique, and really what pseudo-hilo is based off of, is called refined OSM or RSIM. And so OSM is able to get around high frequency noise that's added based on the OSM reconstruction algorithm by essentially applying a high-low based reconstruction where you put a high-pass filter on your pseudo-wide field image and combine that with a scaled version of your OSM image. And so that is essentially what inspired our pseudo-high-low technique. But the problem is that, as Ahmed had talked about, voltage indicators have very rapid temporal dynamics. So a single spike might only show up in a single frame. And so the problem with that is that for all these OSM-based reconstructions, you're using squared subtractions, and the assumption is that the only change in fluorescence that a pixel receives is due to the changing grading pattern. So as you can imagine, that's very bad for very rapid temporal dynamics. So here I'm showing some simulated GCamp transients and the OSM reconstructed response. And as you can see, it's very distorted due to this algorithm. And as you decrease the rise time of that transient, the correlation between the OSM reconstruction and the ground truth decreases. So on the other side, the pseudo wide field image really is just the mean image. And so the mean image applies a smoothing effect. So here I've simulated some essentially motion artifacts for our pseudo wide field and OSM reconstruction. You can see that the pseudo wide field reconstruction has a smoothing effect. And if we look at the algorithm for our pseudo wide field image, well, we can see that we can essentially gain from it a uniform illumination image, which is just the pseudo wide field reconstruction. in the structured illumination image, which is the structured image at each time point. And so that brings us back to halo microscopy. Remember that halo extracts modulation contrast from a uniform illumination image and a structured illumination image. And so this is more robust to distortions from rapid sample dynamics. And it doesn't require precise phase shifts or post hoc approximation. So this is what led to our pseudo-hilo algorithm. It almost seems silly, but what we're really doing is just a hilo reconstruction with the structured illumination image and the uniform illumination image, or the pseudo-wide field image, at each time point. So if you look at your raw structured illumination image manifold, you can create an interleaved pseudo-wide field manifold, which is essentially just applying a 3-frame boxcar average to your entire time course. And then you can perform pseudo-hilo reconstruction at each of those time points. And so when we use that algorithm instead of traditional OSM, we see that there is a much higher correlation between our pseudo-hilo reconstruction and our ground truth simulated transient than OSM. It actually maintained in this specific data over a 98% correlation as we decrease that rise time, whereas OSM falls off. And we see the same thing for motion. Essentially, the pseudo-hilo, really because it's using a pseudo-wide field smooth image, really is just a smooth reconstruction that is not prone to the same distortions as OSM. That's what makes it really great for using in samples that have rapidly changing temporal dynamics, such as voltage imaging. So here I'm showing on the left a Z-stack that was taken with 5 micron steps. And it's going to be above and below an in-focus cell here at depth equals 0. And so if we look back up to depth equals 15, this cell is now out of focus. And if we look at our pseudo-wide field reconstruction for an ROI around that cell, you can see that you can still make out very clear spikes. And, regardless of the spike detection algorithm you're using, be it VolPy or something similar, you're going to still be getting contamination from those out of focus neurons. But if we look at the same exact data with the pseudo-hilo reconstruction, we see something different. The contamination from the out of focus neuron, ROI1, has been decreased. Essentially, it has been the size of the spikes has gone within the level of noise. While the in focus cell, you can still clearly make out the cells. These are recordings taken at 500 frames per second in the visual cortex, and all of this data is using Voltron 2, by the way, I should note. It's really incredible voltage indicator. So looking at 1200 hertz recordings in the neocortex, these are essentially pseudo-wide field and pseudo-hilo reconstructions. We can look at a correlation heat map, which is essentially, these are 80,000 frame recordings. For each pixel, it's correlation with the mean time course, the mean of all images, all of the pixels summed. And in the pseudo-wide field reconstruction, you see a lot of correlation kind of everywhere. But in the pseudo-hilo reconstruction, you can see that the heat has essentially been located to the cells of interest. And that's good, because that means that the activity that we're seeing is coming from the in-focus cells. So here are the time courses that we extracted from these ROIs. And you can see the pseudo-hilo delta F over F is larger than the pseudo-wide field. And the reason for that is that the delta F over F really is the change in fluorescence over the resting baseline fluorescence. And so by that baseline fluorescence includes the out of focus background. So by removing the out of focus fluorescence, we essentially decrease that denominator and increase the delta F over F. Here are some zoomed in windows of the time courses. But of course, nothing in life comes for free. So here I'm showing spike templates of a wide field and pseudo-hilo reconstruct. Or so this is a wide field spike template that is not a reconstruction, and then pseudo-hilo for the same cell, back-to-back recordings, both taking at 900 hertz from PV interneurons. And so while you do see that the height of the delta F over F is increasing, indicating the reduction of out of focus background, you also see a broadening. And that really is because of that boxcar average effect. So the problem, the problem with pseudo-hilo that we have is, well, we can pick up individual spikes. We can't sample frequencies that are essentially we want to go 3 times what Nyquist would be for the spike rate of the cell of interest. So for a PV interneuron, that might be very high. So pseudo-hilo is something that is more useful when there are low spike rates. And so the next steps of this are really to tie it back to the miniature microscope. So right now, our miniature microscopes don't have micro LEDs on board, and we don't have essentially a custom camera that one of our collaborators is developing on board. But we can do calcium imaging with structured illumination. We can do it about 4 frames per second. We have a joke in my lab that GCamp6 imaging at 4 frames per second has very similar dynamics to voltage imaging at 1200 frames per second. You can see in the pseudo wide field reconstruction that essentially, or more so the OSM reconstruction, that the transients have been distorted. I've highlighted in red the specific transient that's distorted. But in the pseudo-Hyler reconstruction, we can gain that optical sectioning capability without having that distortion. So that really is the benefit of this. So the next steps of this project are really just going to be the further development of the miniature microscope, and hopefully if we can improve on the technique a little bit more. So I'd like to thank everyone that I work with at University of Colorado Anschutz, University of Colorado Boulder, and Columbia University, and Alec Thiel, a good friend of mine and lab member who is actually the neurosurgeon that makes the mice that we're using. So thank you, everyone, and it's an honor to speak to you.